I've taken this picture from Google. Okay. So in this representation, these all are particles. All of these are particles, and the thing on the top, the thing on the top is the mass. The mass is a charge, and this is the spin. Now, the concept of spin is very much different in particle physics as compared to classical physics. What does spin in classical physics mean? It means a body is rotating about its axis. The spin of the cricket ball, the spin of the tennis ball. But to make things easy, we have found a nice way to explain the spin in case of a particle physics using a classical approach. I hope you can see this. This is a ball, a mere sponge ball. So, there are particles, as you can see, here are particles with spin of half. Yeah, and you can see here particles having spin 1, and here there are particles having spin 0. So what does this thing spin actually mean? So consider this as a particle. This face is marked smiley. This has a smiley, this face. Now what does spin half means? If the ball rotates about its axis and take exactly 2 complete rotations to return back to its initial position, to the initial point. So what was the initial point? The initial point was this face, which you all can see. If a particle takes 2 complete rotations to again reach to this initial position, then we can say its spin is half. And what do you mean by the spin of 1? Similarly, if consider this as another particle which has a spin of 1. So spin of 1 means if this particle takes 1 complete rotation to return to its initial position, then that particle can be said to have a spin of 1. Right? So this is the concept of spin explained in a very simple way through a classical approach. Now let's focus on the standard model. So this is a standard model of elementary particles. That means these particles cannot be broken down into any other particles. Let me mark this. These are quarks, as you can see in the diagram also, and these are leptons. And let me find the cursor. And all of this are bosons. Now remember, all of these particles are elementary in nature, right? That means they cannot be broken down. I need a blank slide. Here it is. Now, if you consider a broad classification, the subatomic particles are mainly classified, if I'm considering on the basis of interaction, as, let me write over here. So we have subatomic particles. So as they are classified as leptons and hadrons. Yeah, the large hadron collider, that hadron. Now, I said that on the basis of interaction. So, what is the difference between leptons and hadrons? Leptons don't respond to strong interaction. Hadrons respond to strong interaction. Now, these leptons are elementary. That means they cannot be broken down further. But these hadrons are composite, which means made up of elementary particles. Right. Hadrons are again subdivided into two types. One is the mesons and another is the baryons. So, what are mesons? Mesons are those hadrons which comprise of a quark-antiquark pair. That means they are composite particles and they are made up of two elementary particles. These elementary particles are quarks. We will discuss quarks very soon. So, for the time being, mesons are made up of quark and an antiquark. This denotes quark and this is an antiquark. And baryons are a combination of three quarks. So mesons have integral spins. They all have integral spin. That is like 1 or 0. And mesons have an integral spin, that is 1 and 0, and baryons have non-integral spins. So mesons don't obey the Pauli exclusion principle. I'm sure you have read about the Pauli exclusion principle previously, but let me do a recap of that. So, Pauli exclusion principle, it states that for particles having Sorry, I must erase this for understanding. I'm so sorry. Yes. Done. I'm sorry for the inconvenience. Now, states that for particles, I hope you can understand my handwriting. I know it's not too good. Pardon me. Yeah, for particles having half integral, this is not the statement of the Pauli exclusion principle, but this is a reasoning, an understanding of the principle. For particles having half integral spin, no more than uh, one similar particle can exist in the same quantum number. I'm sorry, quantum state. Yeah. So, two similar quarks cannot exist in the same particle. This is what Pauli exclusion principle implies. Yeah. Now we were discussing about the standard model. Now this is the first generation of matter. This is the second generation of matter, and this is the third generation of matter. Now all of this elementary particles, the quarks and leptons, are collectively broadly classified as fermions. Fermions, named after Enrico Fermi. These particles have half integral spins, and they obey the Pauli exclusion principle. So they have half integral spin and obey Pauli exclusion principle. We have already discussed what Pauli exclusion principle is. So, moving on to the right side of the standard model, uh, these these five elements are known as bosons. Bosons are also called force carriers. They carry force and energy through the universe, carry force and energy through the universe. They have integral spins and they don't obey Pauli exclusion principle. So we can say that mesons have some similarity to the bosons since they also do not obey the Pauli exclusion principle. Bosons are also classified as gauge bosons. So this gluon photon, Z boson, and omega boson. These are gauge bosons. They are known as gauge bosons because they have a definite spin of 1. You can see that the spin of a gluon is 1. Here it is, 1. For a photon is 1. For a Z boson is 1. For a omega boson is 1. But for Higgs boson, the spin is also 0. Yeah, it is an integral spin, so it is a boson, but its spin is 0. So that's why Higgs boson is also known as the scalar boson. I think the slide is quite jacked up, so I should erase what I have written till this. Let me erase all these things. Thank you for your patience. Thank you for your patience. Now, let's move to the main topic of today's talk, which is the quark. As you can see in the standard model, uh, it's been marked here as quark. So, what is a quark? A quark is an elementary particle which is found inside hadrons. We discussed hadrons just a few minutes ago. So hadrons are nothing but composite particles which uh, comprise of these quarks. Let's take an example of, let me go to a new slide. So let me take an example. For example, uh, a proton. Yeah, a proton is a hadron since it's a composite particle. So a proton, we have a diagram of proton uh, in one of the next slides. Let me show. Yeah. So this is a proton. I hope you can see the screen. This is a proton, and it comprises of 3 quarks, which means it's a baryon. The neutron on the left side also comprises of 3 quarks, which means it's a baryon too. So both of these are baryons. This is a baryon and this is also a baryon. Yeah. Let's move back to the standard model. Yeah. So we were talking about the quarks. But before we dive into quarks, as I already showed you, presence of quarks inside hadrons, inside protons and neutrons, I would discuss more about it. But before that, I would like to discuss on the eightfold way. Yeah, the eightfold way. Yeah. Uh, let's move on. Let's show what the eightfold way is. So, eightfold way. Eightfold way. So, uh, eightfold way is nothing but an organizing scheme. Scheme for grouping hadron particles. Now, a question arises whether all of these particles are elementary or not. Are these elementary? Or are they made up of constituent particles? Yeah, I'm talking about hadrons. As already discussed, hadrons are not elementary. They are made up of constituent particles called quarks, which are to be discussed in the coming few minutes. Now, let's take in the idea of the eightfold way. Arranging the hadrons, arranging the hadrons uh, into groups or geometrical patterns having same S spin but different charge, different charge or strangeness. Yeah, the strangeness which was discovered, I forgot the year. That's why I told that we don't need to remember the dates really. We need to remember the concept. So, uh, strangeness, right? So, strangeness was found in 1947. Okay, now let's move back to where we were. Yeah. So, arranging the hadrons into groups or geometrical patterns having same spin but different charge or strangeness gives us the eightfold way. This gives us the eightfold way. So it's also a broad classification uh, based on properties like same similar spin. The spin of all those particles is the same, but they have a different charge. So this eightfold way uh, is again described by three ways, three classifications. One of them is known as the baryon octet, which means eight. Then we have a meson monet. Then we have the baryon decuplet. which means 10. We have diagrams of all this here. Now this is the meson octet. All of these are different particles which came as a result of the particle zoo. Now this is the neutron, this is the proton. Now S stands for strangeness. Since we described that each of the particle have the same spin, all of them have the same spin, all of them same spin. But neutron and proton have the strangeness of 0, strangeness number 0. These four particles have the strangeness number of -1. And these two particles have the strangeness number of -2. Whereas these two particles have the strangeness, have the charge, Q is the charge of -1. Now, neutron is, as you know, is neutral. These are neutral too. This means they are neutral. This is the negative sign means that they have a charge of -1. Negative sign means charge of -1. So these four particles, I hope you are understanding, have the charge of 0. And these two particles again have a charge of +1. This plus means a positive charge. Right. So here we have 8 particles. 1, 2, 3, 4, 5, 6, 7 and 8. That's why this is known as the baryon octet. All of these particles are baryons. Right. Now let's move on to the meson monet. Now this is the meson monet. Oh, I should have mentioned it there. Like in meson monet, you have 9 monet. This means 9, right? So we have the meson monet. Starting from the top, these two particles have the strangeness number of +1. These 5 particles have the strangeness of 0. And these two particles have the strangeness of -1. I will clearly explain what strangeness is. Just wait for a few minutes. Like few minutes, yeah. And vertically, these two particles have a negative charge. These 5 particles are neutral. Q is equal to 0. And these two particles have a positive charge. Right. So this is the meson monet, and all of these particles are mesons. This is the chion. This is the pion. Pi mesons are chi mesons. Right. Now let's move on to the baryon decuplet. Now decuplet means 10. So we are dealing with 10 particles. And all of these are baryons. That is, they comprise of 3 individual quarks inside them. 3 quarks inside them. So this row has a strangeness number of 0. This row has a strangeness number of -1. Careful, -1. These two have a strangeness number of -2, and is this has a strangeness number of -3. Can you recognize this element? It's the omega minus, discovered in 1964. Yeah, we read about in the history of particle physics. Now, this is the baryon decuplet. Since we are dealing with 10 particles. Now, moving on vertically, this four particles have a charge of -1. These three particles have a charge of 0, and these two particles have a charge of +1, and this particle has a charge of +2. That's all for the eightfold way. It was just a brief introduction to this topic because I thought that people who are reading about quarks need to know about the eightfold way. Now, there's a nice story behind the formation of eightfold way. The eightfold way, I'm sorry, I mean the formulation of the eightfold way. Yeah. So the eightfold way was given by Murray Gell-Mann and Yuval Niemann. Yeah, Murray Gell-Mann was an American physicist, and Yuval Niemann was an Israeli physicist. Yeah, so they were influenced by Buddhism. Now, in Buddhism, there's something known as the Eightfold Path. So this eightfold path uh, is something which we can find in Buddhism, and it states the ways that there are 8 ways. It states that there are 8 ways, 8 distinct ways in by which a man, can attain enlightenment. Buddhism states that there are 8 ways to salvation. Now, it is famously known as the Eightfold Path. Since the two scientists were very much interested, very much influenced by the thoughts of Buddhism, they famously named it the Eightfold Way. Uh, and as the name stands still today. Yeah. So one thing I forgot to mention in all these things is that one thing is I forgot to mention in this baryon decouplet is that the spin of all these particles is equal to 3 by 2. In case of the meson monet, the spin of all these particles, S stands spin, because this is strangeness. So spin of all the mesons here is 0, and the spin in the baryon octet of all the elements of the baryon octet spin of all the elements of the baryon octet is half. Yeah. Now we are back with the standard model. So we learned about the eightfold way. Now let's dive into the main topic of today's course, that is the quarks. So as you can see in the standard model, there are 6 different types of quarks. Yeah. So they are up, down. Yeah, this is the first generation, this is second generation, and this is the third generation. charm, strange, top, and bottom. And this is the, I mean, order of the mass from from up, increasing from up to, uh, increasing from generation 1 to generation 3. Yeah. So as you can see, this is the mass. I should clear this out at first. So yeah, as I was saying, uh, this is the generation 1, generation 2, and generation 3. Uh, this is the mass of up quark, this is the mass of down quark, mass of charm quark, mass of strange quark, mass of top quark, and mass of bottom quark. Uh, one thing which is to be considered here is the unit. This is in mega electron volt, and this is in giga electron volt. So this is the mass of the charm quark is much greater than that of the mass of the up quark, whereas the mass of the top quark is even greater. Here, this is in mega electron volt. So mass of the strange quark is much greater than that of the down quark, since this is also in mega electron volt, but here you can see it's 4.8 and here it's 95. So a huge difference. And this is in giga electron volt, and 4.1 is giga electron volt. So the top quark is the heaviest quark, and the up quark is the lightest quark. These are the charge. The up quark has a charge of plus two by three. This is plus 2 by 3. The down quark has negative 2 by 3. Negative 1 by 3. My bad. The charm quark again has a charge of plus 2 by 3. The strange quark has a charge of negative 1 by 3. The same goes for top and bottom. Now, one question must arise in the mind, that why are the charges not integral? Why are they 2 by 3, 1 by 3, and all this? I'll show you the reason. Now, as we discussed that, for example, a proton consists of uh, a down quark and two up quarks. Okay, so a proton has two up quarks and one down quark. Up, up, and down. Now the overall charge of a proton is plus 1. Now the charge of this up quark is plus 2 by 3. This up quark is plus 2 by 3. So if we add this, it becomes plus 4 by 3. Whereas the charge of the down quark is negative 1 by 3. So if we subtract it, negative 1 by 3, we get 3 by 3, which is equal to 1, which is plus 1. So this matches the charge of a proton, right? Now the fundamental, we saw the historical approach. Historically, the fundamental entities, the quarks which were first discovered were the up, down, and strange quark. Yeah. So let's represent all this using a simple geometrical diagram. So this represents the down quark, this represents the up quark, and this represents the strange quark. Yeah. So the down quark has a strangeness of zero. I'll explain strangeness just now. Just after explaining this, the up quark has a strangeness of zero, but strange quark has a strangeness of negative one, as the name suggests. The down quark has a charge of negative 1 by 3. The up quark has a charge of positive 2 by 3. And the strange quark has a charge of negative 1 by 3. I'll write it again. And Q equal to negative 1 by 3. So as you can see, if the particle is neutral, then the particle has a overall charge of 0, 2 by 3 minus 1 by 3 is 1 by 3 and minus 1 by 3 is 0, and a strangeness of negative 1. Right. Uh, we consider a particle which is constituted of a down quark, an up quark, and a strange quark. Now, what are antiquarks? Let's take another example. Let's take the anti-quark. Let's take an element which comprises of the anti-quarks of this configuration. Yeah. So we have B bar. This defines the anti-quark of the down quark. Okay. Uh, I think it will not fit in this page. So we'll move into another page. Or we should erase all these things. Yeah. So I think this would pacify. Yeah. I'm sorry. Yeah. So, as I was saying, we consider anti-quark. I mean, a particle which constitutes of anti-quarks of this configuration. So we have the strange quark at the top. Uh, it's better if you consider a line. It's better to understand. Yeah. The strange quark, and we have the anti-quark of the down quark and the anti-quark of the up quark. So these are anti-quarks. Yeah. So the charge of a strange quark is negative 1 by 3. So this will have a charge of positive 1 by 3. The charge of a up quark is negative 2 by, I'm sorry, the charge of a up quark is positive 2 by 3. So the charge of the anti-up quark should be negative 2 by 3. The charge of a down quark is negative 1 by 3. So the charge of the anti-down quark will be positive 1 by 3. Yeah. Mm. And the strangeness will also reverse, but since the strangeness of the up quark was 0, so the strangeness of the anti-quark of the up quark will also be 0. The same goes for the down quark, 0. And for the strange quark, the strangeness will be plus 1, since it was negative 1 for the strange quark. So this is the, representation of the quark and the antiquarks. Now, since we are getting familiar with quarks, let's see the arrangement of quarks in few particles, which were already mentioned while discussing the history of particle physics. So we already discussed about protons and neutrons. Like in protons, you have two up quarks. So we have plus 2 by 3, plus 2 by 3, and one down quark, negative 2 by 3, which equals to plus 1. This is the protonic charge. And for neutron, its neutron consists of one up quark and two down quarks. So it's plus 2 by 3, minus 1 by 3, and minus 1 by 3. So it becomes 0, which is the property of neutron since it's neutral. Neutral. So this proves the fractional charges of quarks. Like the fractional charges of quarks uh, provides for the known charges of composite particles such as protons and neutrons. Now, quarks arrange themselves in such a way that these particles, I mean, for baryons, first generation, like protons and neutrons, they have a spin of half. Let's consider some more, elements. I'm sorry, more particles. So here we have a pion, which was already discussed while discussing the history of the particle physics. Now, a pion is a meson. This is a meson. Since we have a quark and an anti-quark pair. Remember, obviously, in a meson, obviously we cannot have up quark and the anti-quark of the up quark because that would cause annihilation and the particle will cease to exist. Right? We discussed this while discussing quantum chromodynamics that I'm sorry, quantum electrodynamics that uh, when a quark and an anti-quark uh, collide with each other, pair up with each other, then they cause annihilation, and with that annihilation, a burst of energy comes out, which is nothing but photon. So this was described by quantum electrodynamics in 1950. Yeah. So obviously in a meson we have a quark anti-quark pair, but like in pion we have the quark as up quark and the anti-quark of the down quark. This condition is feasible, right? So we have a pion, which is we have a positive pi meson. Yeah. Let's consider we have a positive pi meson. So it is also denoted by pi plus. This was, discussed while discussing the history of particle physics. So it contains uh, U up quark and the anti-quark of the down quark, as mentioned in the diagram. So calculating the charge, we have charge of 2 by 3. It is 2 by 3. And down quark is minus 1 by 3. So anti-quark will be plus 1 by 3. 2 by 3 plus 1 by 3 is 1. The charge of 1 uh, spin. So spin will be up quark and down quark. So spin will be 0. And the strangeness will be 0 plus 0, which is equal to 0. Now I forgot to calculate the strangeness for proton and for neutron. For proton and also the spin. Yeah, yeah, yeah. For proton, uh, uh, I mean, first we will start with neutron. For neutron, the spin is half. So how does the spin of half comes? We have up quark, one up quark, we have one up quark, one down quark. So these two will cancel out each other, and we have another down quark. So this will contribute to the spin half. I'm sorry, half. And strangeness will be again 0 plus 0 plus 0, which is 0. For proton, same thing. Up, up, and down. So these two will cancel out, and this will contribute to half spin. And the strangeness will be 0 plus 0 plus 0. Again 0. Now, moving on to the omega particle. Yeah. So this is a negatively charged particle, omega particle. This is omega minus. So it contains three strange quarks. Yeah, quite strange. Three strange quarks. So the total charge will be minus 1 by 3, minus 1 by 3, minus 1 by 3. Since the strange quark has a charge of minus 1 by 3. Here it is. Strange quark is minus 1 by 3. Yeah. So it's minus 3 by 3 or minus 1. And the spin is again all the three particles are same. So positive spin, I mean spin in the same direction. Since all the three are strange quarks, so same direction spin. So the total spin is 3 by 2. For each of this, it's half. This is half, and this again is half. So half into 3, it is 3 by 2. Right. And the strangeness of the strange quark is negative 1, minus 1, minus 1, and minus 1, which is minus 3. So this is for the omega particle.